All right, hello everyone. As you can see, I've got experiment 8 here, okay, the charge to mass ratio of the electron in my hand. And so I'm going to start by talking a little bit about it and showing you how the equipment is used. So basically, right around the turn of the century, I should say the last century, okay, right around 1900, J.J. Thomson developed the cathode ray tube. And with that device, he was able to figure out the charge to mass ratio of the electron. It wasn't until about a decade later that Robert Millikan was actually able to figure out the actual charge of the electron, okay, doing his famous oil drop experiment. But what we're going to take a look at today is okay, kind of a rendition of Thomson's experiment where we're going to figure out the charge to mass ratio of the electron. So look, in the lab, this lab was written, there's actually 3 different electron beam tubes that are talked about in this lab. Okay, and when you read them, there is the Senko model, there is a telatomic model, and then there is the one you see in front of you here. This is the Electron model. So to shorten this, we're not going to look at the Senko or telatomic. You're only gonna be looking at data and doing the analysis for the Electron model. With regards to the pre-lab questions, you will need to do the first 5 pre-lab questions in the lab to be able to collect the data, but you can skip question 6, okay, measuring the radius of curvature, because that part deals specifically with the telatomic model. So let me talk a little bit about the equipment here, and not just this model per se, but an electron beam tube, okay, sometimes called the cathode ray tube. And you may notice here there is a filament, okay, which exists inside of an evacuated chamber here, this glass bulb, so we can see what's going on. And that filament is kind of like the filament of an incandescent light bulb. It gets hot, okay, and you excite those electrons in the filament so they're moving quite fast, so that when you supply this voltage to it, okay, in a certain direction, you will actually get electrons to leave the cathode, to leave that filament, and they will then travel towards a positively charged plate called the anode. And once in a minute or so, we will turn off the light so you can actually see this better. But in this particular electron beam tube here, I don't know how well you can see it right now. You'll see it better in a second, but you will see the little light there is the cathode. And in this case here, when we turn on that accelerating voltage, that electron beam is going to be directed straight down, okay, into this evacuated tube. And certainly the greater the accelerating voltage, the greater the electron speed, okay, in that tube. What you see here, these big red coils, these are called Helmholtz coils, and basically they provide a fairly strong and uniform magnetic field in the region between the coils. So in a sense, they really behave like a solenoid, but they allow you access to see what's inside. So they're going to produce a uniform magnetic field in the interior region. And one of the questions asks you, to derive this expression for the field in there, which you will need to know. Okay, you'll need to know how the magnitude of that magnetic field in that region. So let's think about the physics here. We're going to end up with these accelerating charged particles, these electrons, okay, which will be accelerated by this voltage. They will have a certain speed, a certain velocity, okay, in this uniform magnetic field created by these Helmholtz coils. When that happens, they're going to experience a deflecting force, as you know, which will behave as a centripetal force, which is going to result in uniform circular motion. So when we turn the lights off, you will see that this electron beam, without the magnetic field, will go straight down. Once we turn on the magnetic field, these charges are then going to experience that centripetal force, and they're going to move in a circular path. There is a little graduated glass rod in there. Hopefully you'll see it with the lights off, which will allow us to measure the radius of that path. Okay, so that we can figure out how big the circle is they move in. Let me just say here that, last thing I'll say here before we turn off the lights, obviously what we can control here, okay, like we said, the voltage that we apply, okay, to that cathode is going to tell us something about, okay, the speed of those electrons when they leave the cathode. And by looking at a coil current here, we can adjust that, which is going to allow us to adjust the current in these Helmholtz coils and therefore control the magnetic field. So you can imagine for different accelerating voltages, that is different electron speeds, and for different currents, that means different magnetic fields, okay, we're going to get circles, okay, circular beam paths of different radii, which we can measure. So from this information, we will be able to figure out the charge to mass ratio of the electron. We now have the lights off, and hopefully you can now clearly see the heated cathode there. What I'm going to do is I'm going to adjust the accelerating voltage to about 200 volts here, and because that's what it tells you to do in a lab. Okay, so right here at about 200 volts, hopefully you can see that that electron beam is directed straight downwards. Okay, and right now there is no magnetic field, so those moving electrons are not experiencing any kind of magnetic or deflecting force. But let's adjust the coil current here. I'm going to slowly adjust that. Okay, and you'll see what happens here. As that magnetic field increases, okay, those electrons start to bend in this circular path. There's going to come a point where we can get this to form a complete circle. Okay, and I want to show you here that when I increase the coil current, okay, the stronger that magnetic field becomes, okay, the bigger that centripetal force is, okay, the smaller the radius of the circle is. Now, we can actually measure the radii of the circle. You can't really do that here. I will provide you with that data, okay, for different accelerating voltages and coil currents here. But let me show you here. Right now we have about 1.14 amperes here. Let's, increase. You'll see what happens as I gradually increase the current and increase the magnetic field strength. Okay, we can form tighter and tighter circles here. Okay, so here, let's keep going up. Okay, coil current of about 2.5 amps. Okay, and that's about the limit we can reach here. Okay, for this accelerating voltage. All right, so like I said, I will be providing you with the measurements that you can't make, things like, the dimensions of the coils, the distance between the coils, the accelerating voltages, and the Helmholtz coils currents, for you to be able to analyze the data.